Hello friends, welcome back to my YouTube channel. In this class I am going to discuss three more problems of chapter 7 of Pekenax Engineering Thermodynamics. That is question number 7.25, 7.26 and 7.27. And these questions are based upon the concept of entropy. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. The question is like this. A copper rod is of length 1 meter and diameter 0.01 meter. One end of the rod is at 100 degrees Celsius and the other at 0 degree Celsius. The rod is perfectly insulated along its length and the thermal conductivity of copper is 380 watt per meter Kelvin. Calculate the rate of heat transfer along the rod and the rate of entropy production due to irreversibility of this heat transfer. Suppose this is the copper rod and it is insulated along its length. There is no heat transfer taking place between this copper rod and the surrounding. This diameter is suppose 0.01 meter and this length is 1 meter. And this is the heat that flows along this length, and we have to calculate this rate of heat transfer. Let it be Q dot, and of course the same amount of heat also leaves this end of the copper rod. So, and the area is pi by 4 d square. This is equal to 7.854 multiplied by 10 to the power minus 5 meter square. And this end's temperature is 373 Kelvin, that is 100 degrees Celsius, and this end's temperature is 0 degrees Celsius, that is 273 Kelvin. Heat is flowing in this direction. Heat always flows from high temperature to low temperature. So now we have to calculate first rate of heat flow according to Fourier's law of heat conduction. Q dot is equal to minus Ka dt upon dx. Minus sign is there just because always whenever heat flows, this temperature gradient is negative. So ultimately the sign will be positive if you take minus sign before this. So this is equal to minus, and the value of K is also given, coefficient of thermal conductivity 380 watt per meter into Kelvin, minus 380 multiplied by 7.854 multiplied by 10 to the power minus 5 multiplied by dt. dt is nothing but the final temperature minus initial temperature. Here the temperature at the inlet and this is the temperature at outlet. So this is 273 minus 373 divided by this length is 1 meter, that is dx, and this becomes 2.9845 watt. This is rate of heat transfer. Now second bit is we have to calculate the rate of entropy production due to irreversibility of this heat transfer. The entropy production or entropy generation takes place only if the process is irreversible. And in case of reversible process, the entropy production is 0. Rate of entropy production is 0. If you apply the entropy balance principle to this system, that is the rod, this will become S in, S dot in, this is the entropy balance principle. Entropy balance principle. S dot in minus S dot out plus S dot generation or production is equal to ds divided by dt. This is rate of change of entropy. Rate of change of entropy. And since this is a steady flow process, because whatever amount of heat flows at this end of the rod, the same amount also flows at this end also. So this is a steady flow. In case of steady flow, if you differentiate change in entropy with respect to time, it will come out as 0. So now here S in is nothing but the entropy, rate of entropy transfer into this rod, that is Q dot divided by temperature at here, heat flows into the system, that is the rod. So here the temperature is 373 minus S dot out is nothing but Q dot divided by 273. This is rate of entropy transfer out of this system plus S dot generation. This is the rate of entropy production or entropy generation is equal to 0. On equating this, we will get rate of entropy generation is equal to Q dot divided by 273 minus Q dot divided by 373. So this is equal to 2.9845 multiplied by 1 upon 273 minus 1 divided by 373. This is equal to 0.00293 watt per Kelvin. So this is the entropy, rate of entropy production due to irreversibility. So next question is question number 7.26. A body of constant heat capacity Cp and at a temperature Ti, the body of constant heat capacity Cp and at a temperature Ti, the temperature of the body is Ti, is put in contact with a reservoir, at a higher temperature Tf. The temperature of body is Ti and the temperature of high temperature reservoir is Tf. The pressure remains constant while the body comes to equilibrium with the reservoir. That means the temperature of body will increase from Ti to Tf, and no matter whatever heat either comes into the reservoir or goes out of the reservoir, its temperature remains unchanged. So in this case also the equilibrium temperature will be Tf only. And so that the entropy change of the universe is equal to this much. And by using this ln 1 plus x is equal to this much, where x is less than 1, we can prove that entropy change is positive. So you see, suppose this is a body with temperature Ti, and this is a reservoir. This is a thermal energy reservoir and temperature of which is Tf, and Tf is greater than Ti. Obviously the heat will flow from this reservoir to this body, because Ti is the less than Tf and heat always flows from high temperature to low temperature. So let Q be the heat that flows from high temperature reservoir to the body, and Cp suppose the heat capacity of the body, capital Cp. Heat capacity is the product of mass into small cp. This is Cp is the specific heat of the body at constant pressure, and product of m and Cp is capital Cp, that is heat capacity. So first we will calculate the change in entropy of body. Before that we must determine what is Q. Q is equal to Cp multiplied by Tf minus Ti. Tf minus Ti. So now if you calculate delta S of body, this is equal to Cp dt upon T, and the initial temperature is Ti, final temperature is Tf. Because once the heat flows from high temperature reservoir to this body, its temperature will go on increase until it attains this final temperature Tf. And the temperature of thermal energy reservoir will not change and it will remain constant at this Tf. So delta S of body will be Cp integral of dt upon T. This is equal to Cp ln Tf upon Ti. And if you calculate the delta S of high temperature reservoir, this will be minus Q divided by Tf. This heat is flowing or heat is going out of this thermal energy reservoir. That's why the minus sign is put before this, minus Q divided by Tf. This is equal to minus Cp Tf minus Ti. This is Q is equal to Cp Tf minus Ti. So minus Cp Tf minus Ti divided by Tf. So this is equal to Cp Ti minus Tf divided by Tf. So delta S of universe is equal to delta S of body plus delta S of reservoir, thermal energy reservoir. This is equal to Cp ln Tf upon Ti plus Cp Ti minus Tf divided by Tf. So this is equal to Cp Ti minus Tf divided by Tf minus ln Ti divided by Tf. So this is equal to Cp Ti minus Tf divided by Tf minus ln 1 plus Ti by Tf minus 1. So this is equal to Cp Ti minus Tf divided by Tf minus ln 1 plus Ti minus Tf divided by Tf. So this is the expression which you are required to prove. You see, entropy change of the universe is, you have to prove that this is equal to this much. So this already we have proved that, and you have got to prove that delta S universe is positive. So let Ti minus Tf divided by Tf is equal to x, as you know Ti is less than Tf, Ti divided by Tf is less than 1. So Ti by Tf minus 1 is less than 0. And you know the expression is ln of 1 plus x, natural logarithm of 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus x fourth by 4. This will go on. So now delta S universe is equal to Cp x minus, I will write this one like this, Cp x minus, in place of this is ln 1 plus x, this is Cp x, because we have taken Ti minus Tf divided by Tf is equal to x. So this expression is Cp into x minus ln 1 plus x. In place of ln 1 plus x, I will write this x minus x square by 2 plus x cube by 3 minus x fourth by 4. I can use this expression only when x is less than 0. So in this case also x is less than 1, and in this case we have found that x is less than 0. Less than 0 means it is already less than 1. So if you expand this, and you see x is a very small number, so we can neglect higher order terms in this expression. So neglecting higher order terms, neglecting higher order terms, delta S universe is equal to Cp x square by 2 minus x cube by 3. Higher order terms will be neglected. So this is equal to Cp x square by 2 1 minus 2 by 3 x, and 1 minus 2 by 3 x is greater than 0 as x is less than 0. Hence, you see, when x is less than 0 means it's a negative number, and minus 2 by 3x is positive. So 1 minus 2 by 3x will be positive. So hence delta S universe, and the x square by 2 is always positive, hence delta S universe is greater than 0, or it is positive. So question number 7.27. So question number 7.27. An insulated 0.75 kg copper calorimeter can containing 0.2 kg water is in equilibrium at a temperature of 20 degrees Celsius. An experimenter now places 0.05 kg of ice at 0 degrees Celsius in the calorimeter and encloses the latter with a heat insulating shield. When all the ice is melted and equilibrium has been reached, what will be the temperature of water and the can? The specific heat of copper is given, and latent heat of ice is given. And the second, compute the entropy increase of universe resulting from the process. And in the third bit, what will be the minimum work needed by a stirrer to bring back the temperature of water to 20 degrees Celsius. You see, this is an insulated container in which water is there, and later on ice is placed inside it. You see, first thing, mass of copper is given to be 0.75 kg. Mass of copper is 0.75 kg, and mass of water is 0.2 kg. Water is inside this copper calorimeter, and mass of ice the experimenter puts inside is 0.05 kg, and initial temperature of ice is 0 degrees Celsius, 273 Kelvin, and both water inside the can and the copper are equilibrium temperature, and both are at 20 degrees Celsius, and in terms of Kelvin this is 293 Kelvin. So, and specific heat of copper is 0.418 kilojoule per kg Kelvin, and latent heat of fusion of ice is given to be 335 kilojoule per kg. So first we have to find out the equilibrium temperature. Inside the calorimeter some amount of water is there, and copper is there. So mass of copper is given to be 0.75 kg, mass of water is given, and both are at the equilibrium temperature 20 degree Celsius. So when ice is placed inside, it means ice will take away the heat liberated by this calorimeter, and will start melting into water, and we have to find out the equilibrium temperature. And the temperature of water and the calorimeter is higher than the ice temperature, and applying this energy balance equation, heat will be taken away by ice, and heat will be given by this copper calorimeter. So by applying that energy balance principle, MCU CCU TCU minus, this is the heat lost by this copper calorimeter, plus this is the heat lost by the water inside this calorimeter, is equal to heat gained by ice. First ice will melt into water at 0 degrees Celsius by observing latent heat of fusion, then it will again, its temperature will rise from 0 degrees Celsius, T minus T0, where T is the final equilibrium temperature. Final equilibrium temperature. So on applying this equation, we will get from this equation minus Mi HFS, latent heat of fusion of ice, minus CWT0 is equal to MCU. Just by taking the T terms into one side and the other terms into other side, we will get the final value of capital T, which is the equilibrium temperature. So equilibrium temperature is nothing but 0.75 multiplied by 0.418 specific heat of copper, 293 is the temperature of copper, that is 20 degrees Celsius, plus 0.2 multiplied by 4.187 multiplied by 293 minus 0.05. Latent heat of fusion of ice is 333 minus 4.187 is the specific heat of water into 273 divided by 0.75 multiplied by 0.418 plus 0.2 multiplied by 4.187 plus 0.05 into 4.187. So this is equal to 277.68 Kelvin, or I can say this is equal to 4.68 degrees Celsius. This is the final equilibrium temperature. So now we have to calculate the change in entropy of universe. Delta S universe is, of course, delta is equal to delta S of water plus delta S of copper plus delta S of ice. So delta S of water first, delta S of water is equal to m of mass of water into specific heat of water ln T. In all these calculations, the final equilibrium temperature will be capital T, because all will be having the same equilibrium temperature. And delta S of copper is equal to mass of copper, specific heat of copper, ln T by T of copper. This is the initial temperature of copper. This is the final equilibrium temperature. Delta S of ice. First, the ice will be converted into water. So for that, the change in entropy will mass of ice multiplied by latent heat of fusion divided by saturation temperature, that is the T0 or 273, 0 degree Celsius, plus mass of ice. Then once it is converted into water at 0 degree Celsius, and then its temperature at that state of water, it will increase to 4.68 degrees Celsius. That is the equilibrium temperature. So it will be delta S ice will be CW, specific heat of water, ln T upon T0. T0 is 0 degree Celsius or 273 Kelvin. Now by putting numerical values, we will get delta S of water is equal to 0.2 multiplied by 4.187, that is specific heat of water, ln 277.68. This is the capital T, final equilibrium temperature, 293. This is equal to minus 0.0449 kilojoule per Kelvin. Similarly, delta S of copper is equal to 0.75 mass of copper into 0.418 ln final equilibrium temperature 277.68 divided by 293, because both water and copper are at the same temperature, that is 20 degrees Celsius. Then this is equal to minus 0.0168 kilojoule per Kelvin. Delta S of ice is equal to 0.05 333 by 273 plus 4.187 ln 277.68 divided by 273. So this is equal to 0.0645 kilojoule per Kelvin. And this is positive because the temperature of ice increases from 0 degrees Celsius to 4.68 degrees Celsius. And once it is converted into water, then its temperature rises. And while being converted to water also, it absorbs latent heat of fusion. So delta S of universe will be summation of these three. This will be minus 0.0449 minus 0.0168 plus 0.0645 kilojoule per Kelvin, and this is equal to 2.8 into 10 to the power minus 3 kilojoule per Kelvin. So as far as the third bit is concerned, थर्ड बीट में अगर हम ये जो फाइनल इक्विलिब्रियम टेम्परेचर से वाटर, इफ यू वांट टू कन्वर्ट दैट इनटू द वाटर टेम्परेचर व्हिच इज एट 20 डिग्री सेल्सियस, हाउ टू ब्रिंग दिस नाउ final temperature is 20 degrees Celsius. So how to bring this equilibrium temperature to that of 20 degrees Celsius? For that, we need to supply heat, but in this case we are not to supply heat, but we have to supply the paddle wheel work. You know, the if you supply paddle wheel work into any system, obviously due to internal irreversibilities, due to dissipation of work into internal energy increase, temperature will also go on. So what is the amount of work, paddle wheel work, that is to be supplied, that to bring the whole system into 20 degrees Celsius, that we want to calculate. And of course the vessel, the whole apparatus is insulated. So first we have to calculate what is the mass of water. Now the ice is converted to water, so the amount of water now is mw. Mw is, initially the mass of water inside this apparatus was 0.2 kg, and then 0.05 kg of ice was there, and once the ice, now ice has melted into water, so 0.25 kg. So now we have to increase the temperature from 4.68 to 20 degree Celsius. So for that, what is the work done? Both the temperature of water and the temperature of copper are to be increased. So amount of work needed is equal to mw cw 20 minus T. T is the now present temperature once they have attained an equilibrium condition, plus mcu ccu 20 minus T. So now this is mass of water is 0.25, specific heat of water is 4.187 into 20 minus 4.68 plus mass of copper is 0.75 into 0.418 is specific heat of copper into 20 minus 4.68. So this is equal to 20.812 kilojoules. This amount of paddle wheel work is to be supplied to this whole apparatus to bring the whole system into a temperature of 20 degrees Celsius.